Hello, future engineers. Welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired, and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. So here is a video on lecture video and sample problem videos on internal forces and moments. This is in preparation to the construction of the shear, force, and bending moment diagrams, as well as the sketching of the elastic curve. So it is important that the free body diagram is correctly made, labeling all the internal forces and writing equations of statics to solve for these internal forces. And finally, and hopefully, you are able to prepare for problems where you can solve by your own and prepare for your quizzes and exams. I hope that this video will help you in your preparations as civil engineering students and allied engineering students in some aspect. So I hope so. Determine the internal forces at points J when alpha is 90 degrees. So here is the given figure. So let's change this because alpha is 90, so that means 780 Newton is vertical. So for the solution, so let's have the tension here. This angle is arctan of 300 over 480 plus 240, 720. Arctan of 300 over 720. And therefore, so this is the load 780 because alpha is 90, so it is vertical. So that's arctan of 300 over 720, 22.62. So we cut the cable and we sum up moments about B. So the vertical component T cosine 22.62. The distance to B is 0.6. The horizontal component, so that's clockwise. The horizontal component is T sine 22.62 and its moment about B is counterclockwise. So minus T sine of 22.62 times 0.72. Then minus 780 times zero point 0.3 equals 0. So solving for the tension equals 845.0 newtons. So we now draw the free body diagram of this portion, including JCDJ. So for the forces, this is 0.24 or 240 mm. Then remember the tension is 845, so this is 845 cosine 22.62, and that is equal to 780 also. So we have the load here, horizontal component 845 sine 22.62, and the loading at D, which is 780. For the internal forces, we have NJ, let's assume it is compression, then up to the left VJ, then moment is counterclockwise as shown. So first, summation forces, the angle, remember, is 22.62. And let's solve this distance x1 by similar triangles. So x1 as to 240 equals 300 as to 720. So x sub 1 is equal to 0.1 meter. So that's zero point 0.1. So this distance is 0.1 as shown. Then this is 22.62 degrees also, same as that. And VJ makes an angle with a horizontal of 22.62 also. So that's 22.62. So summation forces vertical rather, NJ is negative, vertical component is negative NJ cosine 22.62 plus vertical component of VJ, which is VJ sine of 22.62, So summation forces vertical, since 780 minus 780 is 0, so equals 0. Call that equation 1. Then summation forces horizontal, 845 sine 22.62 minus nj sine 22.62 minus vj cosine 22.62 equals 0. So simplifying, we have nj sine 22.62 plus vj cosine 22.62 equals 845 sine 22.62, or 325 if you simplify that. So solving equations 1 and 2 simultaneously, we get nj equals 125.0 Newton. So that's correct. It's compression. Vj is equal to 300 Newtons. Now for the moment, we sum up moment about j equals 0. So mj plus this. So mj plus 845 sine of 22.62 times 0.24. Then this is a couple, which is clockwise. mj is counterclockwise, so minus 780 times 0.3. So I just use 780 times 0.3. We sum up moment about j, but since 780 and 780 constitute a couple, so the moment of the couple is 780 times 0.3. Same is true if you sum up moment here. So minus 780 times 0.4, then plus 780 times 0.1. So it's the same. Solving for mj is equal to 156 Newton meter. So in other words, in this solution, you may ignore the calculation of x1 because it is not used here. I didn't expect that uh, this constitute a couple, but if you sum up moment at j, we get the same result. So that's it for this problem. For the frame and loading shown, determine the internal forces at point J, then point K. So here's the given figure. Take note that if we sum up moments about A, assuming there is vertical reaction here, since the moment of the 250 Newton force about A is 0, so reaction times 160 mm plus nothing equals 0, therefore the reaction here, vertical reaction at C is 0. So we now cut this part and show the internal forces at J. So we have NJ, assume compression. It should oppose to 50. Did VJ up to the right, then moment counterclockwise as shown to counter the moment of 250. So first the angle. This angle, the angle that this plane or this segment of the frame makes with the horizontal is arctan of 20 mm over 80, and that is 36.87. So this is 36.87 degrees. So therefore this is 36.87, and the angle that VJ makes with the vertical is also 36.87. Remember that the normal and the shear force are perpendicular to each other. So 36.87, 36.87 also. So first, submission forces horizontal. So NJ cosine 36.87 plus VJ sine 36.87 minus 250 equals 0 or equals to 50. Call that equation 1. Summation forces vertical, negative NJ sine of 36.87 plus VJ cosine of 36.87 equals 0. So that's equation 2. Solving these two equations simultaneously, we get NJ 200 newtons and VJ equals 150 newtons. Then for the moment, summation moment about J equals 0, MJ minus 250 times 80 mm or 0.08. So MJ minus 250 times 0.08 meter equals 0. So MJ is equal to 20 newtons. Now for the internal force system at K. So if we imagine this is K, the result is the same for NJ and VJ. Since K is closer to C, so it is only MK that changes. So MK is 250 times zero point zero 0.06 only. So at K, we expect the same answer. So we imagine J is also K because it is just aligned. They are just aligned. So NK is 200. So imagine this is K. Then if that is K, then the vertical distance of 250 from K is only 60 mm or 0.06. So Vk is equal to 150 newtons, and Mk minus 250 times zero point zero 0.06 equals 0. So Mk this time is 50 Newton meters. A semicircular rod is loaded as shown. So determine the internal forces at point J knowing that theta is 30 degrees. Also determine the magnitude and location of the maximum bending moment in the rod. So here is the given figure. So by looking at the frame or and rod, we have a two-force body, which is this member here, CD. So there's no load in between. So therefore the force in D is equal to force in CD, and therefore the direction of force is along CD. So call that reaction at D as PDC as shown. It is directed along CD. Then at A we have AX and AY. So this angle, the measure of this angle is equal to 36.87 arctan of this vertical distance 120 over horizontal distance 160. So again, arctan of 120 over 160 is 36.87. So that's AX and AY. So summation of moment about A equals 0. Considering this figure, only the horizontal component of PDC has moment about A. The vertical component passes to A. So 0. PDC cosine of 36.87 times 280 mm, then minus 280 times 320, 160 times 2 equals 0. So 320 moment arm, 160 times 2. So PDC can now be computed. It is equal to 400 newtons. So that's 400 newtons. Then we want to solve AX and AY. So 400 cosine of 36.87 minus AX summation versus X equals 0. So AX is equal to 320 Newton. Summation versus Y, 400 sine of 36.87 plus AY minus 280 equals 0. So AY equals 40 newtons. So let's have this as free body as shown in the figure. So we have the 40 upward and 320 leftward. Then the normal reaction internal force system at J normal. So let's have assume tension to oppose 40. Then shear up to the right as shown. Then moment clockwise. So let's call that point O, moment J clockwise. So this distance, the moment arm of 40 at about J is this distance here, which is radius 160. Then this is also radius, so 160 minus 160 cosine of theta. So this distance, this horizontal distance from J to O is radius cosine theta. So MJ plus 40 times radius 0.16, then minus this distance 0.16 cosine of theta, 0.16 cosine of 30 degrees, theta is 30. That's the moment arm of 40 about J. This horizontal distance here again is 0.16 minus this horizontal projection 0.16 cosine of theta, 0.16 cosine 30. Then minus 320 times 0.16 sine theta. This vertical distance is 0.16 radius sine of theta minus 320 times 0.16 sine of 30 degrees equals 0. So we can now solve for mj. Mj is equal to 24.74 Newton meter. So the question is internal forces. So I computed mj first to get rid of two equations to unknowns. My next plan is to sum up moments about O equals 0. So nj is perpendicular to this radial line. So its moment arm is 0.16. nj times 0.16, then minus the moment, because that's counterclockwise. The moment is clockwise, so minus 24.74, then minus 40 times 0.16 equals 0. So we can now solve for nj. nj is equal to 194.6 newtons. Then we may now sum up versus vertical equals 0. So remember, this is theta also. Then the Vj makes an angle of theta with horizontal, just like that. So summation versus vertical 40 plus Vj sine of 30, vertical component of Vj, Vj sine of theta or Vj sine of 30, then minus Nj cosine of theta, Nj cosine 30 minus 194.6 cosine of 30 degrees equals 0. So Vj equals 257.1 newtons. So there is still one static equation that is not used, summation versus x. We can use that for checking. So mj, this is now for the second part, maximizing bending moment. I leave that to you, the checking summation versus x, to verify these answers. So in general, so theta is unknown this time because we want to maximize and locate the point on the semicircular rod where moment is maximum. So the moment about j, theta is unknown, is mj plus 40. This is horizontal distance is radius in general minus radius cosine theta. This vertical distance, just like this, radius minus radius cosine of theta, which is this. Then minus 320 times radius sine theta, this one. 320 times radius sine theta, which is the same as this. 320 radius was 0.16 sine 30 degrees, although it's also 0.16 here. So simplifying, mj equals 320 r sine theta, then minus 40r, then plus 40r cosine theta. So since we want to maximize mj, let's differentiate it with respect to theta. And the result is 320r, derivative of sine is cosine theta, then plus 40r times negative sine theta, derivative of r cosine theta. Derivative of negative for r, of course, with respect to theta is 0. So 320 over 40 is 8. We cancel out r. So 8 cosine theta equals sine theta. Then tangent theta is 8. Sine over cosine is 8. So tangent theta is 8. So theta can now be computed, 82.875 degrees. Then the answer for theta is 82.875 degrees. Then for maximum moment, we substitute it here. Then remember, r is 0.16 and theta is 82.875. So mj max is 320 times 0.16 sine of 82.875 degrees minus 40 times 0.16 plus 40 times 0.16 cosine of 82.875 degrees. So the maximum moment is equal to 45.20 newtons, and it is located on this semicircular bent rod with theta equal to 82.875 degrees. So it is close to C, just to the left. So the moment, if we cut section C just to the right, the moment is 280 times 0.16, which is slightly lower than 45.2. So that's why this is the maximum moment. Level 14, an archer aiming at a target is pulling with a 45-pound force on the bowstring. Assuming that the shape of the bow can be approximated by a parabola, determine the internal forces at point J. Also determine the magnitude and location of the maximum A axial force, B shearing force, and C bending moment. So here's the given figure. Then remember that this archer exerts a pull of 45 pounds, and therefore, since by symmetry the tension in this string is the same, we will call that T and T. The angle that tension makes with this horizontal is arctan of 32, 16 plus 16 over 24, and that is 53.13 degrees. So let's solve for t by summing up forces x. So 2t cosine of 53.13 degrees, because there are two tensions, equal magnitude minus 45 equals 0. So t is equal to 37.5 pounds. Then let's have this portion C to J or BJ, free body diagram. So take note that there is horizontal distance between J and this vertical line here. So we can solve that by squared property of parabola. So this is the tension, 37.5 pounds. It makes an angle with a horizontal of 53.13 degrees. So let's call that delta. By squared property of parabola, delta as to square of this distance equals 8 as to the square of this distance. So delta as to 16 square equals 8 as to 32 square. So delta equals 2 inches. So that's 2 inches. Then for the internal forces, let's have Nj in compression to oppose the vertical component of 37.5, Vj up to the right, and moment clockwise assumption. So equations of statics, summation of forces x0, y0, then we can solve Nj and Vj. Now the angle that Nj makes with the vertical or Vj makes with horizontal is to be determined first by determining the equation of this parabola. So by squared property of parabola, let's superimpose the axis first. So let's call this the h-axis, and that's the v-axis. So h as to v squared by squared property. So vertical h as to v squared equals 8 as to 32 square. So the equation of the parabola in terms of h and v is h equals v squared over 128. Remember that the slope is tangent of theta, and it's the derivative of h with respect to v. So the h dv equals v over tangent theta is v over 64. Since the value of v at j is 2, so tangent theta is 2 over 64, or theta j. So this is theta j. Then the angle that Vj makes with the horizontal is also theta j. So tangent theta j is equal to V 16, this one 16 over 64. The value of V is 16 at this j here over 64. So theta j is 14.036 degrees, theta j. So summation, so this is 53.13 degrees. Summation forces horizontal. So Nj sine of theta j plus Vj cosine of theta j, Vj cosine of 14.036, then equals or minus horizontal component of 37.5 cosine of 53.13, so minus 37.5 cosine 53.13 degrees equals 0. So simplifying, negative Nj sine 14.036 plus Vj cosine of 14.036 equals 22.5. Call that equation 1. Then summation versus vertical, Nj cosine of upward, so Nj cosine of 14.036, upward also for Vj, Vj sine of 14.036, then equals 37.5 sine of 53.13. Equation 2 equals downward force. So solving equations 1 and 2, we have NJ equals 23.65 pounds and VJ equals 29.1 pound. For the moment, summation moment about J equals 0. So MJ minus horizontal moment of horizontal component 37.5 cosine 53.13. The moment arm is 16. Then minus the vertical component, moment of vertical component 37.5 sine of 53.13, and the moment arm is only 6, not 8. 8 minus 2. So minus 37.5 sine 53.13 degrees times 6 equals 0. So MJ can now be solved. 540 pounds. Now for the maximum axial force, the maximum axial force occurs at C, and that is when theta C is 0. Theta C is 0 at C. The angle that the normal makes with the vertical line is 0. So that if theta is 0, then in this equation, if we have sine of 0, Vj cannot contribute, so that's why Nj is maximum. So Nj cosine of 0 from this equation. So Nj max is Nj max cosine of 0 plus Vj sine of 0, so that's why Vj cannot contribute, equals 37.5 sine 53.13 degrees. So the maximum normal force is 30 pounds and it occurs at C. Then Nj is minimum when theta j is maximum. Theta j is maximum at B or at D by symmetry. So therefore, shear is maximum at B because Nj is minimum at B. When theta j is maximum, then Nj is minimum. So therefore, we solve for theta B. The value of V at B is 16 plus 16, 32. Substitute here. So tangent theta B, which is tangent theta D also, is V over 64, where V at B is vertical distance is 32 over 64. So theta B is equal to 26.575 degrees. So substitute into this equation here, then replace 14.036 by 26.565. The corresponding value of Vj would be maximum because Nj is minimum there. Or in equation 1, rather, negative Nj sine of 26.565 plus Vj, we just replace 14.036, and the right side remains the same because it is the constant here. Then in equation 2, we replace just the angle to cosine of 26.565 degrees, then Vj sine of 26.565 degrees equals 37.5 sine of 53.13 degrees. Equation 4, solving these two equations simultaneously, remember the corresponding value of Vj is maximum. So Vj max is 33.54 pounds and it occurs at B and D. Finally, for maximum moment, it occurs at C because the moment arms of this 37.5 is maximum at C. Since we resolve this into components, so Mj equals 37.5 cosine 53.13 degrees. The moment arm is 32 at C, maximum, plus 37.5 sine of 53.13 degrees. The moment arm is 8 inches, maximum also. And there's no point in the bow where this force is farthest from C except for B and D, the tension. So it occurs at C, the maximum moment, and its value is equal to 960 pound-inch, and it occurs at C. So that's it for this problem. So lastly, knowing that the radius of its pulley is 200 mm and neglecting friction, determine the internal forces at point J, then at point K of the frame shown. So here is the given figure. So before we solve for the internal forces at J, we want the reactions first at A and B. So we have AX expected rightward, AY downward, at B leftward, and upward. So take note that if we sum up forces horizontal, we conclude that AX equals BX. So summation moment about B equals 0, considering the entire system. So AX times 1.8 counterclockwise positive equals clockwise moment 360 times 0.8 times 3 is 2.4 plus radius of pulley 0.2. So the total moment arm is 2.6. So AX therefore is equal to 520 newtons, which is also equal to BX. Now for AY, let's draw the free body diagram of this part. And this is the free body diagram. Let's have the AX and AY unknown. So external reaction will not change direction, only the internal reactions will change direction opposite and equal to the reactions in the adjacent member or connected member. So take note that the tension at D is also 360 because we have frictionless pulley. So that's 360, and the tension here which can be transmitted at E parallel would be 360 newtons also. So we have 360 downward, 360 up to the left, and the reactions at E, EX and EY. So to solve for AY, we must sum up moments about E so that all these forces will not be involved in the moment equation. So AY times 2.4 equals 360 times 1.6. So AY therefore is equal to 240 newtons downward. Then considering the entire free body diagram to solve for BY equals AY plus 360. So BY equals 240 plus 360. So BY equals 600 newtons upward as shown. So we now isolate this part because we can now compute the internal force system at J. But before that, let's solve for this distance and that distance. The horizontal distance between C and J is 0.8 minus radius 0.2, so 0.6. So call that 8 sub C, and this distance 8 sub J by similar triangles. So this distance is 0.6. So by similar triangles, 8 sub C as to 0.6 plus 0.8, 1.4 equals HJ as to 0.8 equals 1.8 as to 2.4. So solving for HC is 1.05 meters and HJ equals 0.6 meter. So for the free body diagram of this part, so the tension 360 and 360, so these are the reactions 520 and BY upward 600. Then tension, then the internal forces. So this angle is 36.87. The angle that this inclined bar of the frame makes with the horizontal is arctan of 1.8 over 2.4. So I just mentioned it, arctan of 1.8 over 2.4 is 36.87. So these are the internal forces, NJ. VJ, that's just an assumed direction. If it is wrongly directed, then it will just give us a negative value. Then MJ. Then the angle that VJ makes with the vertical is 36.87. NJ with the horizontal is also 36.87. So this distance is 0.6 between C and J horizontally. C and J and K and J horizontally. So this vertical distance is from J to there is 1.8 minus HJ, which is 0.6, so that's 1.2. And this vertical distance between C and J is 8 sub C, 1.05 minus 8 sub J, 0.6, so 1.05 minus 0.6, 0.45. So this is 36.87, Vj mixed with the vertical, and Nj with horizontal, 36.87. So summation forces, x equals 0, horizontal equals 0. So horizontal component of Nj cosine of 36.87, which is that, then plus Vj sine of 36.87, then minus 520 plus 360 cosine of 36.87 degrees, then minus 520 equals 0. Simplifying, Nj cosine 36.87 degrees plus Vj sine 36.87 degrees equals 232. Call that equation 1. Then summation forces vertical, Nj is negative, so negative Nj sine of the negative Nj sine of 36.87 plus Vj cosine of 36.87, then plus 600, then minus 360 sine of 36.87 equals 0. So simplifying, negative Nj sine of 36.87 plus Vj cosine of 36.87 equals negative 24. Solving equations 1 and 2 simultaneously. So we have Nj 200 and Vj equals 120 newtons. For Mj, summation moment about J equals 0. So we have Mj plus 360 times 0.8. This is 0.8, 0.2 radius plus 0.6 minus 360 times radius 0.2 plus 520 times 1.2, then minus 600 times 1.6 equals 0. So Mj can now be computed. It is equal to 120 Newton meter. Since the results are all positive, I correctly assign the directions of these internal forces. Then for the internal forces at K, let's isolate this as free body diagram as shown. Then we have reactions, AX 520 to the right, AY 240 downward, then tension here 360, then the internal forces, it should be compression for NK, then downward for shear at K, then moment clockwise as shown. So summation forces horizontal NK is obviously 520, then summation forces vertical 360 minus 240 minus V sub K equals 0. So the shear at K is 120 newtons. Then summation moment about K equals 0. Mk plus 360 times 0.8, then minus 240 times 1.6 equals 0. So Mk is equal to 96 Newton meter. So again, all the internal forces are positive, so that means these directions are correct. So that's it for this problem.